Good morning, good afternoon, good evening. Today I'll be showing you how to make the 3D bounce text. 3D text mesh will bounce and deform based on physics calculation. Deforming portion is pretty simple as long as you have remesh, but I'll also be going over how to make bouncing physics for this effect. So if that might be of interest to you, this video should be a fun one. I'll be using 3D text remesh node group I introduced in past video. Please watch that one first if you haven't made that node yet. Link is in the description. Alright, let's get into it. Alright, before we move to geometry nodes layout, let's go to the output tab and change FPS to 60. You can follow along with 24 FPS, but the deforming animation is smoother with 60. Let's now move to geometry nodes layout. H select all, X to delete. Shift A, add mesh plane. Then, using numpad 7 and 5, go to top orthographic view. Click on new, delete group input. Then, replace it with string input. We will start with single letter, so enter T. Then, pass it through strings to curve and output. Insert a remesh text 3D right after. And use 0.02 and 0.1 for its parameters. Alright, we have now a cleanly remeshed 3D text. Let's prevent recalculation by inserting a bake. From 4.2, we no longer need to save the blend file to bake it, so let's just go ahead and bake. Let's insert a transform geometry and rotate on X by 90 to make it stand up. Alright, there we go. For the 3D bounce effect, we'll separately construct the deformation and bouncing physics. Though it's not quite necessary to create a physics logic in geometry nodes, it is an easy and fun topic to cover. So let's start with deformation. We want to insert a squashing deformation when the letter hits the ground. The shape should look something like this. First, we'll spread the lower portion in XY direction. Then, we'll push down the top to create a squashed shape. Alright, let's get started. We want to control points, so let's realize the instance. Then, we'll calculate the center of this mesh. Add a bounding box and connect the vector mass add from max, then sum it up with min. Connect the vector mass scale and scale by 0.5 to calculate the average of upper and lower bounds. Next, we'll normalize the mesh z height. We'll have the bottom points representing 0 and top points representing 1. Select the bounding box and Ctrl-Shift-D to duplicate with connections. Add a position node and vector mass subtract min from it. Duplicate the vector mass subtract, then subtract min from max. Vector mass divides the result like so. The result is normalized in all directions, so use separate XYZ to isolate Z. Calculation result will be within 0 to 1 based on the point Z position. So let's spread the bottom portion like so. Create a space and insert a set position. Connect and combine XYZ from offset. We'll work on XY direction and Z separately. We'll start with XY direction first. Add a position and connect to vector mass subtract. Subtract the center from position to get directional difference. Connect to separate XYZ and connect only the X and Y to combine. Now, Points are uniformly scaled up in XY direction. We want to change the amount based on height, so insert a vector mass scale. Scale it up by normalized z height we calculated. We want it going in opposite direction, so add a subtract after a separate xyz. Alt S to flip the sockets and enter 1 for the top to flip the normalized values. Now mesh should be slanting in the other way. Insert a power and enter 4 for exponent to make it curve. Then multiply it by 4 to increase its effect. Bottom should be spread out in both XY directions now. It looks decent. Now the bottom is done, let's move to Z direction. All we need to do is multiply this Z with negative 0.5 and connect to Z for combine. Alright, it's squashed down nicely. It might look a bit extreme, but we'll just roll with this. To control its effect, we'll add a mix after combine, and connect the result to B. Changing the factor will result in text deforming. We are pretty much done with deformation, so let me show it in full view. Alright, let's start on bouncing physics. We'll move this group output to the bottom for more real estate. This might look familiar to anyone who watched my fireworks video, but we'll construct physics on point basis. So, add points. Then, add a store named attribute and change data type to vector. First store named attribute will be ACC for acceleration. Duplicate, vel for velocity. Duplicate, pause for position. Then connect them up. Add a simulation zone and connect. Duplicate the 3 store named attributes and move them into simulation zone. Then reconnect. Let's add a set position and connect a named attribute pause so we can visualize a physics effect. Short explanation, left area is initialization, middle is update. Let's start with position calculation. First, add a named attribute pause. Connect to vector mass add. Then, add a named attribute vel. Pass it through a vector mass scale. Then, connect to add. Connect delta time to scale. Plug the result into store named attribute pause. Select these 4 nodes and Ctrl-G to group. Open up side panel with N and rename scale input to delta time. Reorganize a bit, then tab out. Rename node group to calc pause. Next, duplicate this node group. Press this number to make it into a single user, then rename it to calc_vel. Connect up the result to store named attribute vel, then tab to edit the content. Change this pause to vel, then this vel to ACC. We're done with velocity calculation. Now, let's enter gravitational acceleration of negative 9.81 to simulate freefall. Okay, here it is. Alright, let's tweak initial position and velocity now. Raise position up by 2 on Z, and set x velocity to 2 as well. Now the point should fall to the right during animation. We'll move on to constructing bouncing part next. We'll treat the Z equals 0 as a ground plane, and point should bounce back after its collision. In case of no damping, point should bounce back to the original height, then repeat bouncing pretty much forever. In case with damping, height along with horizontal distance should decrease with each bounce. We'll first start by not considering damping. Although we can create bouncing by tweaking velocity calculation, we'll do so with acceleration. It makes more sense in terms of energy, and we also want to use acceleration to control text deform. So, start off by creating some space here. We'll first need a way to judge ground collision. We need to identify this timing. To do so, we can use this calc pause. So duplicate it and bring it to the left. Plug in a delta time and connect result to separate XYZ. Pull out a less than or equal from Z and compare it to 0. This should become true if the point hits a ground plane. We'll connect a switch from store named attribute ACC and plug the result into switch socket. Enter negative 9.81 in case of false. Without damping, magnitude of velocity should remain the same with opposite Z direction before and after bounce. To do that with acceleration, first add a named attribute vel. Then separate XYZ to extract the Z component. Multiply Z by negative 2 and divide its result with delta time. Pass it through combine XYZ Z socket and plug it into true. This should give enough instantaneous acceleration to reverse its downward velocity. As you can see, point bounces back to original height, then repeat. Let's just increase the end frame so we have longer animation. So, let's now consider damping. Energy of bouncing object gets converted into heat and deformation energy, resulting in loss each time it bounces. That's why objects never bounce back to its original height. Let's start by creating damping on height. We can do that easily by inserting a multiplier after this one. And enter 0.9 for its value. As you can see, height decreases as it bounces and appears rolling at the end. Next is horizontal damping. If we want to stay true to physics, we have to consider rotation, static and dynamic friction and such. But I'm going to simplify and take the easy way out. First, prepare a named attribute vel and connect to vector mass scale. Next, we'll promote the height damping factor as a value. Connect to mass subtract. Alt S to flip the inputs and enter 1 to the top value. Multiply the result by -1 to reverse direction. Then, divide by delta time. Connect scale to separate XYZ and connect XY to combine. Then, plug the result of divide to scale to enable horizontal damping. Now the horizontal velocity is reduced each bounce and comes to a halt at the end. Alright, let's reorganize. Add a reroute and select these nodes. Ctrl G to group them up, then rename the inputs. Delta time for this input, damp factor for this one. Clean it up a bit. Alright, let's move on. Tab out and rename it to Calc ACC. Let's use 0.9 for its damp factor, and clean up some more. Bouncing physics is pretty much done. We'll just grab these nodes and Ctrl G to group them. Name it Calc Bounce. Let's now join the deformation and physics. Move the group output back to the top to reconnect after set position. Insert a transform geometry. Then, pull out a connection from Calc Bounce and add sample index. Change the type to vector, then connect to a named attribute pods. Connect the result to translation. Now, the text mesh will hop along the bouncing path. Now, let's control deformation factor with physics. I want deformation to react to z acceleration, so let's check it out. When we look at the value of z acceleration with spreadsheet, it is positive at the point of collision. So let's just use this value for now. Connect the sample index to mix factor. Then connect Calc Bounce geometry to it. Add a separate XYZ and connect Z to value. Alas, named attribute ACC to separate XYZ. We can confirm that deformation is happening at the point of collision. However, it is only at an instant as expected. Right here, at this frame. Squashing part is fine, but let's have it return slowly, mimicking hopping behavior. So let's add a filter functionality to smooth out acceleration. Tab into Calc Bounce. Let's just duplicate the store named attribute and rename it to ACC filter. Alright, we'll add a simple filter logic. First, add a named attribute ACC, which is current acceleration. Connect to vector mass scale. Then, duplicate these two and use ACC filter for this one. This is previous value of ACC filter. Add these two results with vector mass add. Next, let's promote the scale value to value node. Set it at 0.2. Connect the subtract to it and Alt-S to flip inputs. Subtract value from 1 and plug it into bottom scale. This will result in 80% reduction filter. Let's reroute and group these nodes up. Rename the input to filter gain and cleanup. Input 0.2 for its filter gain and rename node group to calc ACC filter. Next, let's tab back out to top and change named attribute to reference ACC filter. Also, add a map range after sample index. Change the from max value to 100 to control its effect. We can see that stretching is now happening in multiple frames. It looks like this frame by frame. And I think it's looking nice. Let's delete the set position that I left for debugging. We'll now try a longer string. Go back to the string input and enter test. Don't forget to rebake at frame 1. Now all the text will deform altogether, but let's change it so they do so individually. We'll make the logic loop per each instance. So prepare a for each element. Place the input side before realize and change the main to instance. Place output after transform geometry. Connect them up like so. Make sure to use the bottom socket for output. We'll now prepare point physics for each letter. Tab into calc bounds, then connect the point count to group input. Return to the top and pull out a domain size from transform geometry. Change component to instance and connect instance count to count. We now have point per instance. Next, connect the for each element index to sample index. There are two sample index nodes, so make sure to connect them both. We still have same movement for all letters, so let's change their initial values. In calc bounce, we'll connect a random value to store named attribute val. Let's use -2, -2, 3 for min, 2, 2, and 5 for max. They should now all behave differently. We'll connect seed to group input so we can change it later. For the sake of this video, I'm setting the initial z position to 1 as well. All letters are now bouncing in different directions. Now, this is fine and dandy if you want letters just hopping around, but I want strings to be readable at the end of animation. Usually you cannot predict where all points will end up when using simulation, but we can calculate backwards using bake functionality. Let's add a bake node after calc bounce. Then, run the animation till all letters stop its motion. In this case, all letters are already at halt at frame 500. So, let's just bake to the last frame. This is the end location for each letter, so we'll just offset the position to start. Ctrl-Shift-D to duplicate these two nodes and bring them down. Connect the geometry output out of bake to bottom sample index. Now, vector match subtract the bottom result from top. This will cause letters to return to original position after 500th frame. All letters should start in different location at start of animation now, and gradually bounce back as animation progresses. Things to be aware since we're using multiple bakes. If we change things like string content or font, we'd want to rebake the first bake node. We'd also need to rebake the second bake node after running through animation, if anything before it has been altered. For example, if we change the seed, we'll need an animation run through and update. Before we wrap up, let me make a final modification. This node tree is pretty much FPS independent, except for one part. Filter calculation in calc ACC filter is dependent on delta time. Thus, if we switch to other FPS settings, the effect will be influenced. So let's try to make it completely FPS independent. For the calc ACC filter in calc bounce, enable clamp and connect bottom socket to group input. Then rename it to delta time. Tab out and connect delta time to it. Setting the filter gain to 10 should result in similar result. Here's a render result comparison of 60 and 24 FPS. Though there are subtle differences in simulation, They're pretty much behaving the same without having to alter parameter settings. Alright, let's wrap it up. This is the top layer. Let's take a look from the left. Next is calc bounce. Calc ACC. Calc vel. Calc pause. Calc ACC filter. So, this was an example of using remeshed 3D text within geometry nodes. In order to perform things like 3D text deform and geonodes, it is convenient to have remesh functionality as a node group and not just as a modifier. Alright, this was a long one, but I hope you had fun and hope to see you in the next one.